Hey everyone, welcome to day 2. My name is Etienne Lowe. I'm from ZO Spice, and it's a pleasure to again be introducing the expert speakers for today. Following on the exciting talks of yesterday, we are looking forward to some great talks today, that's for sure. Just a reminder, please, that any questions can be asked in the Q&A tab during the presentation. Please make use of that capability. Our first expert speaker for the day is Torsten Bondo, who will be speaking on water resource management, monitoring and sustaining. Torsten is the Business Development Manager at DHI. From 2015 to 2017, Torsten was a co-founder of Sensonomic, a company using modeling of satellite images and in situ data for developing services for the private and agricultural sector. Before Sensonomic, he worked at the European Space Agency's industry section in supporting the Earth or the European Earth Observation Service industry. Here he was a technical lead and facilitator on a number of ESA contracts in support of mostly developing organizations and international finance institutions. In his current job, he works with innovation and business development at DHI and continue to explore how satellite images can support real-life applications. Since June 2018, he is one of 14 members of the Danish National Space Committee, counseling the Ministry on Space-related matters and the Danish participants to ESA. Torsten, over to you. Thank you very much.
Well, thank you very much, Etienne, and thanks to you for giving me this opportunity to talk. My name is Torsten Bondo. I'm based in Denmark, where DHI has global headquarters. I have both a business and research background, and as Etienne said, I work with business development at DHI. DHI is a global water management research company, a not-for-profit company, and today I will talk about how a traditional water resource managed company as DHI that was founded 65 years ago in 1955 can benefit from Earth observation data and how we work with Earth observation data in this water resource management company. So first I'll say a few words about the DHI Group. Then I'll go on to talk about Earth observation at DHI and give you some examples and some industry perspectives on water resource management and Earth observation. I'll present some success stories and also some challenges on how we work with data. So first I'll let you know what DHI is. DHI is a global water resource management company, 1,200 people and offices all around the world. We are working with agriculture, climate change, surface and groundwater, urban water, environment and ecosystems. And then we have sort of 4 pillars on how we work with these sectors and industries. We work with the development of software products. We are responsible for the development of the MIC software suite, which is sort of the standard hydrological modeling software that generates roughly 20% of our income, a revenue of around 20 million euros. And then we have, as part of this, also water data that goes into this modeling software that we also sell occasionally. This is where, for instance, the remote sensing data goes into the modeling software, and we work directly with the DHI Group to develop services and solutions within that domain. But we also have a classic sort of consultancy business that generates the most of our income. This is mostly big donor projects where we work on regional and large-scale management projects related to water resource management. And then we have a number of sort of other areas related to marine, coastal, offshore products. So over to the remote sensing part of this. DHI has a daughter company called DHI Gras. This is where I'm nested. This is the company that's responsible for doing remote sensing at DHI. We have right now a 20-year history, which means that we actually are one of the sort of older remote sensing companies in Europe. And as you can see from the right-hand side map, we have global references and projects and applications implemented in more than 75 countries all over the world. So how do we work with remote sensing at DHI? With DHI having a large focus on hydrology, it's this picture here presents very well how we work with remote sensing at DHI, since it also lists the challenges that we face. Hydrology is all about monitoring river flows, runoffs from rivers, risks for flooding, monitoring levels of dam and steering levels of dam, and also sort of looking at the overall picture on how these river flow systems and dams and influence the people living alongside these rivers also. What has happened over the last years is that this has gone from sort of a more of a modeling regime into a regime where we now can utilize remote sensing data. So we work with the modelers now on delivering precipitation data, soil moisture data, evapotranspiration, and all kinds of proxies related to water level, water storage, and water quality. One good example here is the case of our work in Myanmar. We work with the local government on setting up a decision support system for the Irrawaddy Delta that covers a large part of the land. The Irrawaddy Delta has a sort of a timely seasonal effect in the sense that it goes over the riverbanks and has highly modular dynamic nature. With new Sentinel data, we can track this nature, see how sandbanks move, see how settlements should best be placed, and feed that information into the decision support system. So I think this is a good case example of how we can work with a traditional decision support system that's based on hydrological model and use new remote sensing sources. Another example is something that we are starting to look more and more into. This is altimetry data. There's a very nice altimeter on board of this Sentinel-3 that enable us to look at new innovation in terms of river flow forecast. River flows are very interesting in the sense that if you have a problem happening upstream, you can now, with the new altimetry data, foresee the water level of the river upstream and help to predict what will the water levels be downstream. This is more a puzzle, as you can see, as you have to sort of knit together information both from the modeling side, but also from the satellite side in terms of finding the right overpasses of the altimeters. We not only use Sentinel-3, but also the other existing American satellites that can do altimetry. This also feeds into a decision regarding to reservoirs and dams, where we can track the water levels of the reservoirs and the dams over time using these kinds of altimeters. So this is an exciting new change for this, as altimeters normally have been utilized over open ocean and large surface areas. We now see potential for going even at river level and smaller reservoirs also. One area that we are also starting to work in and are getting a lot of attention these days is irrigation. And the reason for this is quite simple. The precision agriculture is a big market. It has an estimated market value of around $10 billion. This market is expected to grow over the next many years, and that growth is going to be governed by big data, IoT and drones, and of course satellite data. One of the reasons why this is happening is that we have climate change happening, and that farming and the water use coming from irrigation takes up a large percentage of the water use globally. Alone in US, 80 to 90% of water use is coming from irrigation. And this affects groundwater. You have groundwater depletion. You also have the fact that some people who extract river waters for their irrigation can affect farmers downstream also. So this problem has to be handled, and there's both a sort of climate change perspective in order to handle this, but there's also an economic incentive to develop solutions that can better tackle these issues. So this is something that we are working very heavily on these days, both from a hydrological modeling perspective, but also from a remote sensing perspective. So I'll show you this strange image here. The black line represents an irrigation scheme in Uganda that we have worked on. We won a grant from Microsoft and National Geographic Society to investigate how we can estimate water use in this irrigation scheme, to be able to say something about how is water utilized for these individual parcels that is in this irrigation scheme. This looks very coarse and looks very random, but it's state of the art in terms of what is possible, both modeling wise and remote sensing wise. What we are doing here is that we are merging different satellite data. We are merging thermal data from the Sentinel-3. We're merging with Sentinel-2 optical data in order to downscale this sort of thermal information coming from the thermal sensors into the same grid as the Sentinel. There we're using machine learning in order to downscale this, and use also topographic information in order to do that downscale. Once we have done that downscale, we actually have thermal information that on the ground, and thermal information is needed to say something about how much water escapes from the plants. We also need to utilize meteorological data. There we use wind, we use humidity, we use wind speed, and we use crop canopy structure and crop type. And on top of that, once we have all of that information, we need to put that into a model to actually get the water use from that crop scheme. But once we have that, the potential is quite big, because now we can look at global crops, water availability for different crop types, and also combine that with decision support systems in order for the farmers and irrigation schemes to take informed decision. The same technology is also valid for hydrological modeling of water use in larger dam projects and in larger irrigation scheme, in order to see how best to utilize water in those schemes. So this is an extremely interesting technology we expect a lot from. We are still at an early stage here, but we think that we have a good handle on the technology. We get good absolute accuracy and have compared that to in situ measurements. What we need is sort of the whole wrapping of this into information products that can benefit the farming industry. And this is a challenge, because the farming industry is both conservative and need to be informed about the use of these kinds of remote sensing products, and find the value in this, and convince the value that what we are providing here makes sense for them. So expect to hear more from us in this area over the coming years. We can, with the new sensors, also go further down in terms of resolution. And here's an example of what we can do with irrigation farming, related also to precision farming. So here we have a true color composite. We have the leaf area index, which is the crop canopy structure, and we can utilize the same kind of modeling capability to get out information about the crop water stress and the water deficit. So this is an example of that. And how do we do that? I think the whole enabling of crop type assessment has come from the Sentinel suite of satellites. What we are working on is better and improved crop type information. We get that by analyzing time series of data. And by time series of data, we can get the crop type, we can get the leaf area index by different models, in order to get that crop relevant information that we need for our models in irrigation. This portal that you're seeing here is a very interesting case that we are having with the EU Common Agricultural Policy, where we are the first in Europe to roll out national scheme for providing governmental support to control how farmers are being subsidized for their crops by EU. So here we are utilizing Sentinel data to give information about start of season, crop type, crop growth, and harvest, and a number of other features. The blue dots you see in the left corners show the overpasses of the Sentinel. And we are also working on bridging those days where there are no information with other sources or forecasting. So that's a very interesting area also, and which very much relates to the whole irrigation domain that I was talking about. Another example of how we can utilize irrigation is in terms of water licensing. This will come in many countries over the next couple of years or decades, that water becomes in shortage and there will be needed to either pay for the water or to sort of get allocations in terms of volume for how much water you can extract for irrigation. We set up a trial case in Malawi where we used remote sensing data to pinpoint where the irrigated farms were occurring. This we can analyze using time series again to see how the irrigated crops compare to other crops. And this gives us an information both on the illegal use of irrigation data, but also on the legal use of irrigation. And combining that with some hydrological modeling, we can infer a lot about water use having these kinds of information systems. And this will allow the government to set up better and more precise use on water use and better handle climate change in the years to come. So this kind of licensing systems is something that we expect will happen in the coming year. And it's still on a trial basis, and it's still something that we need to further understand. Soil moisture is very interesting also. It also links to irrigation, but also has other impacts and uses in the hydrological domain. The reason why I bring this up is that we are here using radar data to analyze soil moisture. This allows us for cloud penetration, as most of you know, and gives us the potential to supplement our sort of irrigation solutions with soil moisture derived, radar-based derived soil moisture. And here's an example of how we are now able to get that down to a parcel level and compare that to parcel level soil moisture data with in situ data. There are all kinds of challenges related to soil moisture in terms of radar processing. You can have many different effects, especially in terms of crop type and crop structure that can affect this kind of signal. We are trying to analyze this on a crop type level, where we subtract sort of the typical signals from from a crop type in order to get that information that we are after in terms of soil moisture. So this is of course interesting, since we are able to scale this up. We can then look at parcel level and larger scale patterns in terms of soil moisture, which is also linking into better climate forecast, and is very much also a climate change agenda, but also an agricultural issue. One of the things about soil moisture is that we need to sort of go from the top soil moisture that we get from radar-based methods. Right now, the Sentinel has a C-band, which means that it only penetrates into the sort of top centimeters of the ground. But since we have those hydrological models and software at DHI, we are able to sort of convert that information into volumetric soil water that is asked for or needed by the farmers to drive their decisions. So I'll now turn to something that's also very relevant for DHI, namely water quality. Water quality is traditionally difficult to assess from space. The technology has improved quite a lot over the years, and we are now starting to sort of get cost-effective solution that can also offer that sort of temporal need that these decision makers need in order to do better point sampling. So what we see here is an example where we have a time-based sampling of a lake, and are able to sort of see how these remote sensing data can benefit for this governmental case that we are looking at here. Here's a nice picture also showing what kind of spatial resolution we can achieve with these data. So what are the challenges in terms of water quality? One of the things is that remote sensing for water quality should not be replaced by in situ networks, but it may be able to complement them. And it can sort of create solutions that are both scalable and cost effective. Some of these solutions are very difficult to validate, and they need in situ data also. So I think we are still seeing the first uses of this. It has been going on for many years. There are good examples of this, but I hope to see more cases of water quality from space in order for this to drive decisions also. One thing that we've worked on quite a lot in the recent years, both in EU projects, but also supported by the European Space Agency, is shallow water bathymetry. What we are doing here is that we are doing inverse modeling. We are taking high resolution satellite data that are taken at a certain point in time where we have good locations in terms of visibility down the water column. We need to correct that for water glints and wind effects. But once that is done, we can also get to an information layer on the shallow water bathymetry using kind of inverse modeling. This we worked on for 3 to 5 years now, and are starting to get really good results here also. This is relevant and accurate until approximately 10 to 25 meters depths, depending on conditions and clarity of the water. In Scandinavian murky waters, for instance, it's only valid to 6 to 8 meters. But it can really offer something for a lot of stakeholders here. One of the reasons why that is that there is no good solutions on shallow water in order to get that seabed topography. What is a known method is going out with a motorboat and dragging a diver behind you in order to get that information on the water bottom levels. So this is definitely both a cost-efficient supplement to traditional methods, but it's also a challenge in the sense that people who get these maps, they are relying on the navigational charts where they can where they can get legal information on navigations, and that legal information is not right now allowed with using satellite-based Earth observation data. So it does not allow for sort of navigational purposes, although there are some meteorological and mid-ocean offices that are starting to look into this. For instance, the NOAA and the UK Met Office is starting to look into how can they utilize remote sensing data to create sea charge, because there are so many places in the world where sea charge and navigational charge are very very hard to get by and very difficult to navigate after, and they are backdated in terms of time. So this might be often the only real possibility for getting extra information. So here's an example in terms of accuracy. What can we achieve? Here's shown an image from the Palm Islands in Dubai. And on the right-hand side, you see the bathymetry as compared to measurements. And this is a good case. We really get good results on the bathymetry. This is from a very clear water, but we are also able to get good results from clear waters in Greenland. Where we are also able to get good shallow water bathymetry. And this case here up in Greenland, if you look at the navigational charts from the, for instance, the eastern side of Greenland, you will find that they are often 500 to 1 kilometer wrongly positioned in terms of geo accuracy. So getting access to this kind of information can be a very good supporting information to the navigational sea charge, even though they are not sort of legally allowed to navigate after. So this is a very interesting field also, which shows the value of getting good timely data that is has a new timestamps on. And what we have done now is putting this data in use in a portal where people can download this. And one of the reasons why I show you this is, of course, to advertise this, but also to show you the trend that is coming in terms of the remote sensing products also, that we now are coming to a stage where remote sensing products can start to become more off-the-shelf product and not only become sort of project solutions or one-offs. Historically, I think we still have a tendency to deliver remote sensing projects in one-offs and project solutions, and the most of the competitors we have and the private industry and that we are competing with are looking towards these products and off-the-shelf product that we have managed to get out here with the bathymetry. So this is a tendency that I think will come more and more, that we see the maturity or the maturing of the remote sensing products into something that is more commercial, more on demand, and hopefully more utilized also. This is still early days also for us in terms of the uptake of this, but we hope that it's going to be growing over time once remote sensing data is starting to be more used. So I can see my time is slowly ending and I have a few more slides. One aspect of this is very important. In shallow water, you have a lot of changes in terms of sand deposit. This is the case where you have, for instance, a river flowing out or you are close to an area with lots of turbidity or sediment settling. If you have to try to navigate over a navigational chart, you will simply find they're wrong because the sand deposits have changed over time. So this is where timely and updated information about bathymetry can make a difference. What we have just done is also scaling this up in terms of habitat mapping, also looking at what kind of environmental parameters can you assess from space also. It's a limited number of classes that you can verify, but we have, with Sentinel data, mapped green and dense vegetation, submerged aquatic vegetation, and mapped shallow sand deposit, and scaled that up to the whole coastline of Denmark, which is quite big since we have a number of islands also. So this is another case of how the scaling up is becoming more and more easy with remote sensing data. And I think this is an important aspect in terms of environmental management, and we have the Danish Environmental Ministry looking into this and finding this data useful for their planning. I'll end on, let's call it a more global note on the UN SDGs. DHI is a non-for-profit agency. We are also having an affiliation to the UNEP, meaning that the UNEP DHI Center is a sort of a UNEP affiliated center. What that means is that we are right now responsible for helping UNEP on the SDG 661 on water-related ecosystems. So we more particularly help UNEP populate data and host right now the SDG 661 app on water-related ecosystems. This is very interesting. We are hosting also the JSC global surface water data, many of you know, and some other data related to freshwater ecosystem. I urge you to have a look at this app that is global, available data on freshwater ecosystems, populated by JSC, NASA, JAXA on mangroves, and a number of big organizations that help populate this. We have done a global wetland map that is also part of this, I think this kind of reporting into the UN system is extremely nice and rewarding in terms of helping the countries drive better decisions on fresh water. So I think I'll end there. I think my time is pretty much up also now, and leave with some few questions. And also leave you with my email. So if there's anything, please reach out. You can also find me on LinkedIn if there's something that we need to discuss related to what I've shown you here. So I'll wait a few more minutes to see if any questions pop up, or else I think this session is concluded. And I'll open the floor for questions, as I said. I'll wait another 30 seconds for questions, and then I think we should end this session. I think everybody's focused on the American election, and I hope that you will go and see this presentation again. Again, my email is there, and you can reach out for me if you have any questions. So thank you very much, everybody, for connecting. I'll sign off here now, and wish you a good end of this conference. Bye for now.